Hello guys, in today's video we are going to learn how to build a simple electric motor. But don't forget, this is Osem Global. If today is the first day you are seeing our video, or you've been seeing our video but you are not following our page, please follow our page, like, comment and share the video. Follow our page so that you get more updates anytime we drop a new video. Let's watch this video.
I'm going to show you how to build this simple electrical motor and also explain how it works. When we apply a voltage to the motor's electrical terminals on the commutator, it begins to rotate. As we increase the voltage, it rotates even faster. So, how does it work? This simple electrical motor consists of the following parts: the base, which holds everything together, the stator, which remains stationary and holds the magnets in position, the supports, which contain some bearings to hold the rotor and shaft in position and also allow a smooth rotation. There's the shaft, which sits between the two bearings and rotates. We can make use of this rotation by attaching gears, fans, pulleys, etc. Then there's the rotor, which is attached to the shaft. This has a coil of wire wrapped around it, and the ends of the coil connect to two separated metal plates known as the commutator. There are two wires lightly touching the commutator plates, and we use these to apply a voltage to the coil. When we connect it to a power supply, the electrical current will travel up the wire and into one of the plates. It then flows around the coil and out the other end. This flows into the other commutator plate, where it flows out of the other wire. This causes the whole thing to rotate. This motor rotates because of the interaction of the different magnetic fields between the rotor and the stator. We know that magnets interact. The alike ends will repel and the opposite ends attract. We can cause a magnet to rotate by moving another magnet close to it, causing a repulsion or attraction. When we pass an electrical current through a wire, we also create a magnetic field around the wire. If we reverse the direction of current, we reverse the magnetic polarity. We can see that by placing some compasses around the wire and passing a current through the wire. The magnets will rotate and align. If we reverse the direction of current, the compass needles also rotate. If we place the wire between two magnets, the magnetic field of the wire will interact with the permanent magnet, and the wire will be forced to move because of this interaction. If we change the direction of current, the wire moves in the opposite direction. We can tell if the wire will move up or down by using Fleming's left-hand rule. As an added bonus, you can also download my free guidebook for this also. Links down below for that. If we hold out our left hand and point our thumb upwards, our first finger straight ahead, and our second finger perpendicular to the first finger, the second finger points in the direction of conventional current, from positive to negative. The first finger points in the direction of the magnetic field, from north to south. The thumb points in the direction the wire will move. In this example, the current is flowing towards us, and the magnetic field is going from left to right. So, with our hand aligned with these, our thumb points upwards. The wire therefore moves upwards. In this example, the current is flowing away from us. We need to therefore rotate our hand to align with it, and we can see that our thumb now points downward. Therefore, the wire will move downwards. If we wrap the wire into a coil, the magnetic field becomes stronger. Each wire continues to produce a small magnetic field, but these combine to form a much larger, stronger magnetic field. We can place a compass at either end to see it forms a magnetic pole. We can reverse the magnetic field by reversing the direction of current. If we allow an electromagnetic coil to rotate freely, when we place an alike pole of a permanent magnet near the coil, it will be repelled away and the opposite end will be attracted. It will then magnetically align and stop rotating. We could then keep flipping the direction of current so it is never able to align, and therefore it just keeps spinning. Instead, we could improve this by spreading the coil out over a wider area between two permanent magnets, and instead of rotating a battery, we could use a commutator to keep flipping the direction of current to cause the non-stop rotation. Our rotor is doing exactly this. The wires are producing a magnetic field when we pass a current through them. The magnetic fields are then repelled and attracted to the permanent magnet. These magnetic fields are then repelled and attracted to the permanent magnets, but the gap in the commutator causes the current to reverse direction every half turn, so it can never magnetically align. I've designed this model using some 3D CAD software, which we can then use to manufacture the parts, and I'll talk you through how to build this in just a moment. So now we are ready to turn our design into a real-world product. You can make one of these out of wood, but it looks much more professional when 3D printed. For the rotor coil, I'm going to use some 0.22mm diameter enameled magnetic copper wire. The enamel coating electrically isolates the wires from each other. This means the current has to flow through the entire wire. Otherwise, it will take the shortest route possible and we wouldn't get a strong magnetic field. We take our wire and we tie it into a knot through the hole in the rotor. Make sure to leave plenty of excess wire and tape the excess to the side of the commutator. Then start wrapping the coil in the clockwise direction. You can give it as many turns as you like, but 400 to 600 turns will work very well. I'm using 600 turns for this design. Then just cut the end and also tie it into a knot through the hole in the frame on the opposite side, again leaving plenty of excess wire. Tape this down also. Your rotor should now look something like this. For the commutator plates, I'm going to use some 22mm copper pipe, and I use some pipe cutters to cut off a section around 20mm long. Then we need to drill a hole all the way through both sides. Make sure the hole is near the end of the pipe section. Then we place the section of pipe into the vise and cut along the length of the pipe. Then turn it over and cut along the opposite side, and we should end up with 2 commutator plates. You should also clean these to improve the electrical connection. Now take the ends of the wire and remove the enamel using some sanding paper and/or a lighter. Be careful not to snap the wire though. You can now tie the wire into a knot through the hole on the commutator plate. Then take some superglue and glue the commutator plate to the rotor. I've placed some guidelines on the rotor to help me align this. Make sure the commutator plate is attached to the nearest side of the coil. Then do the same for the other side. Using a multimeter in the continuity function, test the 2 commutator plates to ensure there is an electrical connection between the 2 plates via the coil. Now slide the rotor assembly over the shaft from the commutator end. I'm using a 5mm diameter stainless steel rod, which is 200mm long. This will give a good tight fit. I've marked the base out onto some plywood, and using a table saw, I'm going to cut this out. You can also 3D print this part if you want. After a few minutes, it should look something like this. As you can see, I've also drilled some holes for the screws, as well as the commutator wires also. For the support arms, I've gone for a dual arm design, which distributes the stresses and vibrations down into the larger countersunk screw blocks, which are joined together. The blocks are positioned away from the center line to make it more rigid for left to right movement. But as the arms are connected to one half of the block, we get some spring action for back and forth movement. Then we place a bearing into the holder, which will be a tight fit. We use these because if we just place the shaft into a groove, the vibrations will cause it to lose its position. So we enclose the shaft to prevent that, but there will be a lot of friction. So we use a bearing to keep it in place and rotate it smoothly. I'm using the 16mm diameter bearings as I just had these spare, but there are better versions available. For the assembly, we screw the front support into place and then hold the shaft and rotor in the bearing while fixing the rear support into place. Now spin the shaft to test that it rotates smoothly. Then we can attach the stator arms into place also. Once ready, push your magnets into position. ensure that the North Pole is facing inwards on the left and the South Pole is facing inwards on the right. If your magnets are not marked, you can use another magnet or a compass to find the polarity. Then we need some wire for the commutator arms. You could use some bare metal paper clips, but I'm going to strip some single core electrical wire and use that. We place it through the hole and then wrap it around. And then we bend it a little bit just so it's very lightly touching against the commutator plates. Now rotate it slowly to check that it touches each plate but isn't touching anything during the gaps. Now we are ready to connect it to a power supply. I'm using a DC bench power supply set at 12 volts. I place the positive on the left and the negative on the right. Then, when I turn it on, the motor starts to rotate. We can increase or decrease the voltage to change the speed of rotation also. It spins very fast, but it's not a very powerful motor because it's just a basic design. Notice that we can also see some sparking occurring on the commutator, especially with the lights off. This will damage the surfaces over time, so play around with the unit and try to keep this to a minimum. There are lots of ways to improve this basic motor. Let me know your ideas for improvements in the comment section down below.
This is the basic way of building a simple electric motor. Thank you for watching. Follow our page for more updates.